In time, we can start our third presentation for this session. This is Witter, a library for white box testing of introductory programming algorithms. Ooh, you are coming in. That's good. And Afonso, the stage is yours.
Thank you so much. Before I begin the presentation proper, I would just like to point out that my co-author André is right there in the audience. So if there's any questions that I feel like he might be better suited to answer than I am, I'll definitely tell him to come up here and take the pressure off my back. So I'd just like to tell you a little bit about the things that we'll be wittering on about today. If any of you are familiar with the expression, that's going to be very funny. Otherwise, please ignore it. So I want to discuss a little bit about one of the problems that we've identified with automated assignment assessment in introductory programming courses. We're going to talk a little bit about that, and then we're going to talk about the approach that we've developed to tackle that problem. We're going to talk a little bit about what it is, how it works, what we've implemented so far. I want to show you all these cool things that already work, some examples of how it works, and then at the end we're going to leave a little bit for what we've planned to implement in the future, and then a little bit of time for discussion and suggestions, which we very much appreciated. So the main goal of our work is to identify and tackle one of the problems with automated assessment of assignments at introductory programming levels. So what is this problem that we think we've identified? Is that usually when at an introductory programming class you're evaluating students' assignments, you do it in a black box manner, which I assume everyone's familiar, but for those, if anyone isn't, that means that the assignment only takes into consideration the outputs of the code. And while that works for a lot of implementations, we feel as if for students that might not be descriptive enough to gauge what the errors in their code were in a straightforward way. They really don't take into consideration many aspects that could be relevant. For example, I reckon most of you have probably either taken or are currently teaching, I don't know, like an introductory algorithms and data structures class. That might be relevant to like see the algorithmic complexity of what the student has implemented, like how many loops I've executed, how many array operations were executed, and usual assessment solutions really don't take that information into consideration. And while you can technically and usually augment some, for example, I'm sure most of you are familiar with JUnit for Java. While you can generally augment those kinds of solutions, by, for example, if you want to measure the running time of a student's program, that's usually quite easy. You just use a timer or a clock that the language provides. But if you want to go more in depth, it usually gets very complicated very quickly. There's things that you can gauge in like static analysis, maybe if you do metaprogramming or reflection. Some of you might be familiar with that term. And if you want to go really in depth, you can do code instrumentation, but that is just very, very specialized, and it's a headache to implement. So it's really not accessible to most practitioners or instructors. So obviously that raises problems and frustrations. For example, I'm sure most of us have either gone through that or have students going through that right now. This raises a ton of frustrations. So if I have a student implement an assignment and I tell them, oh, your function's wrong because I was expecting it to output 100 and output 50, okay, that's all fine. That's true, but like, I don't know why it output 50. Like, why did it output 50? I don't know. Like, I thought it was right. I don't know why this is the way that it is. Or like, okay, I knew it was going to output not the correct result. Like, I don't know what I'm doing. I'm really not familiar with programming. I've never done this before. But I actually needed a tool to tell me what was wrong and how I could have improved. And if it just tells you, oh, the result was wrong, that's why you got it wrong, that's not very helpful if you don't know what you're doing, really, if you're at a base introductory level. And of course, this raises frustrations like, oh my God, I really wanted to help me. I really wanted to know what was wrong. I wanted the tool to be able to guide me a bit more. And we found that usually leads to frustration from the student side, which is obviously something that we want to avoid. And then obviously from a lecturer standpoint that I feel like some of you might relate to, when you want to grade the assignments of maybe a class that has like 500 students enrolled, you can't do that manually. It's not feasible. So you have to come up with an automated solution. But I think one of the main concerns that you might have is, okay, how am I going to write tests that cover, I mean, in theory, potentially 500 different solutions, right? You cannot possibly account for every single minute detail that students could change. Or I don't know, like tell them to implement a specific algorithm and they implement another algorithm that does the same thing. If you only check the results, then obviously it's going to produce the same thing, but you want to check that they implemented the algorithm that you want them to implement. So how do you check that if the only thing that you're taking into consideration is the result of executing the code? And then finally, as I've talked about augmenting these solutions, you can be worried that maybe, okay, if I want to augment my solution, do I really have to go and take time off of grading to learn all these extremely difficult solutions? Obviously, that makes it not very accessible to most instructors. Like, you have things to do. You can't go and stop teaching to go and learn a new specific avant-garde library that allows you to test these things. So how do we think we can tackle at least some of this problem? So we've developed Witter, as I've said, which is a library for white box testing of introductory algorithms. And from what I've described so far, obviously it's developed with students and lecturers in mind. And our main goal is to make the process easier on both sides. So from the instructor, we want them to be able to easily specify test cases for student assignments, including those in-depth ones that I mentioned, without having to have specific knowledge of what actually goes on inside. And then from the student, obviously we all know students don't really want to have that much work, so we don't want them to have to do anything differently. They just submit their code. The code that they've already implemented, the usual thing that they do, they don't need to do anything differently. They just submit the code, and that's what's evaluated. Essentially, what Witter does is it takes the instructor's solution, which we'll analyze in just a little bit, and it takes the student's solution. It executes and compares the two, does its magic that we'll analyze in just a bit, and then at the end we get a list of feedback results that lists some things such as the tests that were passed, what metrics we were evaluating on the student's code. If they were wrong, then what was the result that I was expecting, and what was the result that was actually produced by the student's code. And these, of course, seem very standard for any evaluation solution, so I'd like to give you a little example of how this could actually be used in a classroom environment. So say that you're an instructor and you want them to implement some algorithm that you want to assess. Basically, what you have to do is what you already do. You develop your own solution, right? You want to have a reference solution that you or yourself develop. So you develop that, then what you do, or what we want you to do, is annotate your solution with some extra information about what should be tested. So you implement your solution, and all you have to do is add some annotations in comment format that specify what should be tested. We'll go a little bit more in depth about this in a second, but I can just give you a quick rundown. So what this piece of code is specifying is that for that procedure that we call sort, just descriptive example, it's going to run it for 3 different inputs. So with these 3 arrays separately, then for each of those, it wants to keep track of how many array read and write operations were computed during the execution of the method, and we also want to check for any side effects that were produced on the argument that was passed. Obviously this structure, as you can see, if you're familiar with it, follows the usual Java annotation syntax. This was both a practical and a design choice. In the design standpoint, we know that Java is a very common language, so most instructors will probably be familiar with this syntax. And then at the university that we teach at, they learn Java in their first year, so it will be probably very accessible to them as well. As for the student, they don't really need to do anything differently. They implement the algorithm, and then that's what gets graded. They don't need to do anything differently. So with this in mind, what we can actually measure so far is what I've just told you. Instructors provide their annotated reference solutions. Student provides their regular solutions. And as for things that we can measure, so far we've implemented the measuring of things like return values, which you can use for obviously regular black box testing. And then if you want to go more in depth, you can measure some white box results such as the side effects on an argument, how many loop iterations were run, how many array and objects were allocated, how many times was an array read or written to, and how many recursive calls were executed. So to make this a bit more clear, I'd like to give you some examples. So a very standard, simple example. Let's say you have the student implementing a recursive factorial function, right? So this is probably what most of you would do if you were programming in Java, just a standard implementation. You might do n = 1 here instead of 0, but that's not important. So what we're saying is that the student needs to implement this code, and what we want to test is to pass the integer 5 to this function. We want to check its result first and foremost, and then additionally we want to check that the students, we want to keep track of the students' recursive calls, and then what this one here means is that the number of recursive calls in the student's code needs to be within a margin of 1 of ours. Again, because you can do n = 1 or n = 0, they're both equally valid base cases of recursion, so we don't want to restrict them to doing exactly like we do, so we add a little margin of error. Say maybe the students, first year student, maybe not very familiar with recursion yet, so they try to sneak by implementing an iterative solution. So, basic factorial iterative solution with the added artificial defect that we started the loop here at 0. I don't know, maybe a student's very used to doing loops starting at 0, it's very common, but they forget that they're multiplying things here, so their result is always going to be 0. And then once we pass those 2 solutions to Witter, this is the feedback that gets outputted. And I want to point out that these are not artificially constructed examples. Well, they are in the sense that we had to come up with them, but this feedback was not written just for the conference. We actually implemented the tool up to a point where we could test these, and this was actually the produced output. So what can we tell from this? Obviously, their function is not implemented in general, like it doesn't compute the factorial. Why? Because for the factorial of 5, we were expecting 120, but we got 0, so there's a mistake there. But then where we can check that their algorithm itself behaved unexpectedly was that they didn't implement it recursively. Why? Because we were expecting 4 recursive calls within a margin of 1, but they didn't execute any recursive calls. So immediately we can tell that they implemented an iterative solution. So that gives us much more information that we could gather from just a purely output-based evaluation. Another standard example that you would find in many introductory algorithms classes, the binary searching algorithm, which I'm sure all of you are familiar with. Let's say the instructor provides this solution. Very standard. I'm not going to go into details of the code. Let's just note that what we want to be tested here is we want to find the number 1 in this array, and then another test case, we want to find this number in this array. And to check that the algorithm does what we want it to do, we want to keep track of the number of loop iterations that were computed. Again, maybe the student is very familiar with a binary searching algorithm, so they try to sneak on by using the linear searching algorithm. Much more easier to develop, but it's not what we want them to implement. So this is the code that they provide us, just a regular linear search implementation. We run those 2 solutions through Witter, we get this. So obviously, in here, the black box tests are going to pass, because they're both searching algorithms, so if we want to search for a certain value, they're both going to either find it or not find it, because they're both searching algorithms. So from only that, we wouldn't be able to tell that they didn't implement the correct algorithm. But if we look at the more in-depth metrics, so namely the loop iterations, we can check that the algorithm certainly doesn't match what we implemented. We don't know which one it is, but we just know that it doesn't match the one that we wanted them to implement, because we were expecting either like 4 loop iterations and we got 8, or we were expecting 3 and we got 1. You got the idea. Final example. I don't want to bore you too much with tons of code on screen. The insertion sorting algorithm, another one that we have special contact with in our class. I'm a teaching assistant for an algorithms class, so this is, I see this every day. I ask students to implement insertion sort, and I provide them with a solution that looks like this. And let's say that I want to test it for simplicity. I'm just going to test to see if it sorts this array here. And to guarantee that their algorithm is correct, I want to test the number of array read and write operations. And I want to check what side effects the procedure produces on the argument that was passed. So I'm expecting it to be sorted. So I'm expecting 1, 2, 3, 4, 5. So the student doesn't really like insertion sort. I'm assuming that they're very, very nasty here, so they implement selection sort. So this is a standard implementation. And when we run those 2 solutions through Witter, what we see is that obviously the black box test is going to pass. The side effect on the argument is going to be the same because they both sort it. They're both sorting algorithms. They just don't do it in the way that I want to. And I know that because when I look at the number of array read and write operations, it doesn't at all match the algorithm that I wanted them to implement. So again, what I want you to take away from these is that from the purely black box test, we would not be able to take any conclusions about the algorithm that the student implemented, only that it produces the correct result. But if we look at these 2, then we can tell that the algorithm, surely something must differ here, right? So how is this all implemented? I wanted to pique your interest by showing you examples first, but now I want to talk a little bit about how the magic happens under the hood. So Witter runs on another library, a library called Strudel, which was developed by my co-author André, that basically provides an interpreter that allows us to listen for detailed code execution events. So it executes the code as an interpreter. It basically simulates the JVM. And it lets us listen, for example, to loop iteration events or method call events. Lets us listen to several code execution events. And what we do is, I'm going to show you in a diagram in a little bit, but what we do is we capture that listening system. We gather information as the code executes, and then from that we construct our so-called evaluation metrics. Which brings me to something that I want to mention. It's not in the slides, but I'll talk about it in a little bit. For the annotating of our code, we developed our own little grammar using Antler. We call it the test specification language. Sounds fancy, doesn't it? It's just a simple grammar that we use to specify those annotations. I'm not going to go back. To specify the annotations so that we can actually save the information that we want to test. And then we use the Java parser library to parse the arguments on the annotations that pass the arguments to the test case. We use the Java parser library to parse that information that we can then pass to Strudel that actually interprets that code. So essentially, the workflow for the code being executed and the listening of events that I just mentioned is you take some piece of Java source code, you pass it to Strudel, that loads it, interprets it, constructs an AST, an abstract syntax tree, and then interprets it. So it runs the code, and then obviously it runs it, so it has access to the outputs of the code, and that's what we use to do black box evaluation of the algorithms. And then where we really do our magic is that we hook into the listening system of Strudel, and we can access those code execution events to construct the white box evaluation that I mentioned. Obviously, this is all very cool. I might be biased, but I think it is very cool. But there's still a lot of stuff to be implemented. For instance, we want to implement the capturing of additional runtime metrics. Obviously, you know, recursive calls are cool, return values are cool, array reads and writes. For example, in the example that I showed you about reads and writes, it might be easier to reason about something like array swap operations. At least in introductory algorithms context, it's very common for one of the cost models that we use for algorithmic complexity to be the number of array swap operations. So that might be easier to reason. Obviously, the more metrics that we can capture, the more information that we can give the students, which is also one of our goals, which I'm going to get to in a little bit. I feel like I'm going to get to a lot of things in a little bit. Aside from array writes, we could also check for variable roles, for example. Say in that factorial example that I showed you, I think it would be interesting to be able to measure that the variable that ends up as the return value, that we could check that it actually acts as an accumulator of the result, for example. And of course, we would appreciate any feedback and ideas, which I'm hoping will come along in the discussion phase. Another thing that we want to implement that we assume is probably going to be the most difficult one is stateful testing, which basically means that we want to run sequences of instructions and have the state of the test persist between the two. This, of course, broadens the scope from just static procedures to data structures, which would also be extremely useful in a data structures class, which is also introductory. We do think that this will pose quite a challenge because not only will we have to find a way to annotate data structures with comments that let us specify solutions that should execute sequences of instructions and persist the state between them, but we'll also have to change the way that we provide the feedback to the students, because obviously if you're running 5 or 6 methods on the same data structure, it doesn't suffice to just say, oh, expected this and got this as I showed you in the previous examples. So we think this is probably the biggest feature that we want to implement next, but we also think it would be the most challenging one. Again, I mentioned that this was developed with students in mind, so obviously we want to encourage them to be autonomous and creative. So if we restrict them to a single correct solution, that goes against the exact opposite of that goal. So we want to be able to specify the inclusion of multiple reference solutions, and we don't really think this will be challenging. Just add some annotation that specifies an alternative, then run the student's code against all of them and choose whichever gets the best result. It really doesn't matter there. But this, of course, goes along with the fact that we develop this with student creativity and autonomy in mind. We want them to learn. So if we're restricting them to a single solution, that's super restrictive. That doesn't go along with our goals at all. And then on that note, of course, we have to run tons and tons and tons and tons and tons and tons of tests. We want to really assess how Witter affects the learning progress of students at this level. So we want to see if the inclusion of white box feedback actually lets us access information that could have gone unnoticed in typical black box software testing solutions. If that information does get passed, we want to see if the students can actually use that information to reach correct solutions faster or in a better way, if it is beneficial for their learning. And of course, we're going to have to do some work on how we structure the feedback because we want it to be readable and understandable. So if you just give them a mess of, I know Feline talked in her presentation about the EOF expected, like, we're going to have to do some work on the feedback so that we want it to be understandable for students that might have not have ever coded before, and they still have to take this class. So we want to do tons and tons and tons of tests. The part of testing and how it affects the learning process is probably going to be the focus of my master's dissertation. So I don't know, maybe we'll see each other again, I hope. Yeah, that's really all I had for you today. Thank you so much.
All right, you know the drill, group discussion. All right. Lively discussion. Time. Oh, that works. Lively discussion. Time for questions. Raise your hand as usual.
I feel like you got the sneak peek, though, from the co-author.
Oh, sorry.
Oh, thank you. No, actually, I was just explaining to him what we are doing, and what we are doing is using an interface, given that you use Java. So we would, instead of working on an array, we would have a sequence list, whatever interface, and have then the students take this as an argument and work on it. And then, of course, when I'm testing, I plug in my own class, which can then completely track whatever's happening. Is there... So I like about your approach, because that I would love for my programming class, where I really want to force students to use certain programming constructs. Where in the algorithm class, I'm more interested in the order of process. Do you see a particular benefit on the technical side that you check in the algorithms class, for instance, whether they're how they're accessing the array in an order, or would you see it equivalent to use an abstract interface?
Okay, so it's actually interesting that you mentioned that example about modifying arrays, because that's one of the things that actually motivated the development of Witter, was that I wanted to assess if students actually implemented the correct sorting algorithm. So what I was doing was I was introducing my own class that kept track of the intermediate states of the array. But what I was finding is that, they can loop from left to right, or they can loop from right to left, or they can loop, starting from the middle and doing. So there was a lot of cases that we could that you'd had to take into account. And also what I was doing with my class, or what I tried, was that if I didn't run the code and checked what happened, I would have to do static analysis, which was a headache. So what we ended up concluding was that it would be easiest to just supply a multitude of reference solutions, maybe even just implement some construct that you could add into the body of the method. Says, oh, this can be also in the other order. And then all you have to do is execute the code and just does the comparison automatically for you. You wouldn't have to actually specify the test that takes into account, oh, the array must have been this and this and this and this and this. You do your solution, and then it just compares automatically as the code executes. So I guess it saves some work. Thank you for the question, by the way.
Yeah, so thanks for the talk. So you're using your solution as the ground truth, but, people make mistakes when writing solutions, and when I do this as a teacher, I almost always make mistakes in my reference solution in the first try.
Right.
So then I use my own test to fix my own implementation. Mm-hmm. But if you're using your solution as a ground truth, I would assume you sometimes run into trouble with being wrong.
Okay. Well, I would argue that you can you can input your solution as the ground truth into our tool once you verify that it actually works. So you can test your own solution, and then once that's all nice and verified, you can then add it into our tool, and then that's used as the truth to verify student assignments, because you're assured that your solution already works.
Okay, but so I can't really.
But I get your point. I'm not trying to discredit you.
No, I get it. But so I have to use another tool to test my solution and then plug it in. So I can't do it within your tool.
In order to be certain that it would not, that you wouldn't have any errors on your part, I guess you would have to test your solution beforehand. Yes.
So isn't that a reason to just let me write the expected result in the test within the annotation? So I have the test as well there.
I guess it would be. We did try that initially, but well, do you want to help me out here?
That's a good point. I mean, why not make a self-test? Yeah, I think it's a good point. We discussed that. It's something easy to do, and it's like a pragmatic reason. So
yeah,
I agree with the suggestion.
Our initial implementation actually just had the annotations where you specify the arguments and then comma and then the expected value. So initially, the first alpha version, you implemented that, but then we switched over to it comparing to your reference solution. Because I think what we ended up arguing was that, okay, the professor's already going to have his own solution, so they don't need to do anything. Just slap some comments on there and use that as a reference,
No, it's a good defense, I think.
Yeah. Thank you.
Thank you. So I have a laundry list of questions for you. Tell me.
Okay.
Tell me when to stop.
Oh God, I'm scared now.
So some of the metrics that you're using, you're counting this and counting this and that, but I could see this completely different implementations producing the same matrix. So I'm going to take your factorial example. If I wrote that in tail recursive form, I would get exactly the same metrics the same measurements that you're getting, but it's not written in the way that you're prescribing, which is using structural recursion.
I guess you're right.
Right? And then related to that, think about something like quicksort, for example, right? If I get to pick, if I don't pick, I get to pick the pivot, right? Which one I want. Depending on how I pick the pivot, you're going to get different results.
Yes.
But it is the algorithm that you want.
But one of the things that we thought about in that regard was why we added the margin of error. If I just go back a little bit, maybe to show you. When I described that for the factorial implementation, we added a margin of error for the factorial's recursive calls.
To one.
I guess in any sense, we can just specify whatever number we want. So if we want like, oh, if it's within 20 iterations, then it's technically right. That might be a bit exaggerating, but you could, you don't have to restrict to a specific.
Yeah, so I'm going to give you something to think about, right?
Oh, God, okay.
Think that the vector is already sorted.
Okay.
Now, if you always pick the first element as the pivot, it's a completely different performance as if you pick something else that will more evenly balance the two subtrees, the two subsets that have to be sorted.
You're right. Okay.
Okay, so just food for thought.
Thank you so much. Yeah.
Yeah. And the other question I have is, what about exceptions? Are you thinking about right, programs have exceptions?
We have not yet, because obviously this is like a proof of concept. I'm going to implement more things and then analyze how it affects students. That's going to be the basis of my dissertation. It's just sort of a prototype to demonstrate the practical feasibility of implementing this as a library that could be integrated into other systems. But of course, if we want a full-fledged release implementation, then we would have to think about things like exception handling, or if the exception is meant to be thrown, then we would have to catch that and accept it as a correct solution. Obviously, in a release scenario, we would have to, but for this prototype, we have not handled those yet. Thank you, though.
Yeah, food for thought.
Oh, of course, yeah.
All right, I guess, well, one very last quick question, and then we wrap up, so we don't eat into the break time as we did for the lunchtime.
Yeah, just a quick question. Thanks for the presentation. I asked it in the table as well. It's about the scale of of the feedback that you get with this tool, and in relation to the size of your program or algorithm. So maybe you will have another algorithm, a bigger one, or multiple algorithms, depending on your assignment, of course. And then you will get also a lot of different metrics that you as a teacher, bringing you back to the motivation, you could also have a hard time knowing what's happening there.
Okay.
So what's your thought on that?
I think when we were developing this, we were taking into consideration what we could see at the university that we work at, and what usually happens in introductory, like intro to programming or algorithms and data structures, is that assignments are very, very isolated. So one assignment could be, okay, implement quicksort, or one assignment could be implement insertion sort, or one assignment could be implement binary search. So we usually give them very small, isolated, specific assignments. So that's where we focused our attention for now, because of course we're going to want to run tests later, so it pays to have something that can already work with what's usually happening at our university. But of course, if you have like an implementation that needs 20 functions to be implemented, obviously you're going to get like a feedback that's going to be hard to read. Yes, that would be a problem for bigger implementations, but that's not what we were focusing on for now. It would need to be addressed if we wanted to support bigger implementations, of course. Thank you.
All right, let's thank the speaker once more.